This is the United Aircraft TurboTrain, a new dimension in travel, born of the space age, based on the technology of flight, capable of speeds greater than 170 miles per hour. The TurboTrain was created to help solve the growing problem of getting from the downtown area of one city to that of another, quickly and in comfort. The TurboTrain was conceived and designed by United Aircraft Corporation, one of the world's leading aerospace firms. The train is being developed and marketed by the Sikorsky division of that company. The company put more than 2 years of research and engineering into the gas turbine-powered, fully articulated aluminum train before construction was started. This 17-foot model, for example, was extensively tested in a wind tunnel to prove out the aerodynamic design of the TurboTrain. The heart of the TurboTrain is an aircraft-type gas turbine engine, the ST6, produced by United Aircraft of Canada Limited. This is a full-scale model of the engine, which weighs about 300 pounds, but can produce more than 500 horsepower. The operation of the gas turbine engine is basically simple. Air enters here. It is compressed in this section. Fuel is injected and burned with the air here. The result is a highly energized, rapidly expanding gas. The gas is directed through a free turbine. The free turbine is spun at a precisely controlled speed by the gas, similar to the operation of a windmill. The spinning turbine produces the power to turn the shaft that drives the train's gears. The gas turbines in the TurboTrain are fully developed and are members of the world-famous Pratt & Whitney aircraft family of engines. In the aircraft version, the engines power a number of turboprop planes and helicopters. The engines also have other applications demanding great reliability and unusual toughness, such as in this boat, which raced to a sensational victory on the high seas. And the turbo car, which recorded such an extraordinary performance on the racetrack. In the TurboTrain application, from 1 to 4 engines can be placed in each dome section, depending on the power needed to drive a train of given size and speed. 3 engines are used in this schematic of the propulsion system. Shafts from the engines power the right-angle gearboxes. The right-angle gearboxes can receive power from 2 engines in tandem. Power from all the engines in a power dome car is funneled into this mechanism, the center mixing gearbox. Shafts from the collector mechanism provide power for the gearbox, which turns the train's axles and wheels. To produce electrical power for lighting, air conditioning, heating, and other onboard purposes, one engine drives an alternator through one of the right-angle gearboxes. For operation in New York City tunnels, the TurboTrain is equipped with a 3rd rail pickup and electric traction motors. TurboTrains are structurally similar to airplanes. They are made mostly of aluminum. Large beams running the length of each car help form the great strength of the train. Aircraft structural design and production methods enable these lightweight cars to easily withstand 800,000 pounds of hydraulic force applied to test their strength, a requirement of the Association of American Railroads. The TurboTrain begins to take shape. TurboTrain is ready for its first test run. The first TurboTrain, essentially a prototype for others that followed, was tested a full year before it was outfitted for passenger service, making it one of the most tested trains ever built. The speed of the train was increased in increments until a top speed of 170 miles per hour was achieved. Brakes were tested again and again. Emergency stops were simulated. The brakes were purposely punished more than they ever would be in regular service to prove out their consistent reliability. Ride quality was tested extensively on both welded and jointed rail. The ride quality was carefully measured with the latest equipment. One of the major engineering innovations that contributes to the TurboTrain's smooth ride is the suspension system. Instead of two axles at the end of each car, the TurboTrain has a single axle between two cars, greatly reducing weight and friction. The new system enables the train to round curves with passenger comfort and safety at speeds up to 40% greater than conventional trains. The system is mounted on guided axles which follow tracks around curves. This model demonstrates the difference between a conventional car, shown here, and the TurboTrain. Note first the difference in the height of the cars. Passengers sit about 1.5 feet lower in the TurboTrain than in a conventional car. The center of gravity of the TurboTrain is much lower than that of a conventional train. Centrifugal forces cause a conventional car to lean outward on curves, resulting in passenger discomfort. But the TurboTrain banks inward like an airplane, resulting in much greater passenger comfort. The Power Dome car has a pendulous suspension system also. It too banks inward on curves. The TurboTrain can be operated with superior performance over conventional equipment on any existing, well-maintained track. And TurboTrains can be operated for less costs per seat mile than regular trains, up to 30% less. The reasons for this are many. First, they are constructed of aluminum with use of other lightweight materials throughout. They weigh less than half the weight of conventional diesel-powered trains. This means they require much less horsepower, even for much higher speeds. Higher average speeds also help save money. Initial top speed for passenger service is about 120 miles per hour. This greater top speed, plus faster curve speeds and faster acceleration and braking, permit much greater utilization of the equipment. Another feature is easier maintenance. The TurboTrain was designed to be maintained like an aircraft. At scheduled intervals, wearing parts such as engines, air conditioners, and wheels are quickly replaced with spares and repaired in the shop so the train doesn't have to be taken out of service for long periods of time. Still another feature which helps in the overall economics of the train is its bidirectional capability. Each TurboTrain has two Power Dome cars, one at each end. One car pushes, another pulls. TurboTrains do not have to be turned around, thus saving switching costs and time. The streamlined front of the Power Dome car is actually a nose door, covering an automatic coupler, enabling multiple unit operation of two or more trains. To give a train more passenger capacity, two trains dock together like some of our space vehicles. After the docking, passengers can walk all the way through the train. Each Power Dome car and each intermediate car carries about 50 passengers, depending on the particular arrangements desired by an individual railroad. The interiors are luxurious, like those in the first-class section of a jetliner. Fold-down tables enable passengers to eat at their individual reclining seats. The air conditioning system exhausts directly above each passenger. Truly, this is the most comfortable ride ever experienced on the rails. TurboTrains have been assigned to operate between Boston and New York on the New Haven Railroad. In a demonstration of high-speed ground transportation, sponsored by the United States Department of Transportation. The Boston-New York TurboTrain schedule is 3 hours and 15 minutes with 4 intermediate stops, a reduction of 1 hour from previous best schedules. Canadian National Railways ordered TurboTrains for operation between Montreal and Toronto. The passenger service offered on this run is said to be the finest and most luxurious in the Western Hemisphere. Canadian National's turbos reduced this run from 4 hours and 59 minutes to 3 hours and 59 minutes. Still further reductions are expected as operational experience is gained. In both the United States and Canadian programs, United Aircraft is providing the TurboTrains under lease maintenance agreements. Unsurpassed in passenger comfort, swift, sleek and smooth, this is the TurboTrain, truly a new way to travel.